Hello everybody and welcome back to our AP Physics C class, this time from my living room. The new normal would be for us to do some online direct instruction, and this would be my way of doing it. I hope you're safe and you keep yourself healthy, and I hope you establish some routines for your life as we are moving into these uncharted territories. Well, today I want to talk about the RC circuits, and obviously an RC circuit has a resistor and a capacitor and a battery. And let's just draw this circuit together. We have the battery, then we have the resistor here of resistance R, and then we have the capacitor of capacitance C, and obviously we want to have a switch here which at time equals 0 it's going to be closed. As we close the circuit, charges will be flowing through the circuit, and the capacitor is going to be charged positively on this upper plate and negatively on the lower plate. And at one point when the capacitor is fully charged, the capacitor would not be able to accommodate any charges, and the capacitor will act like a switch. Before that happens, at the time equals 0, when we start charging the capacitor acts like a wire. And the questions that we have are: what is the intensity in the circuit, and what's the charge that's mounted on the capacitor plates? So if we want to conceptualize what's going on there, we might be able to say, well, the intensity starts with the maximum value, and then as the capacitor is charging, the intensity is decaying in value. So we have a maximum intensity at time equals 0, and let's call that I0, and then we have a decay in the value of that intensity. And then when it comes to the charge itself, we have no charge on the capacitor. As we start the charge flowing through the circuit, there is no charge on the capacitor. At equals 0, charge is 0, and at a certain time the capacitor is fully charged, and then the maximum charge would be Q, which is your Q final, because initially you have no charge. Now empirically we can say that there is a time when we can say the capacitor is fully charged, and it seems like that time for the capacitance to be the capacitor to be fully charged, that time is 5 times a constant of this circuit RC, which is called tau. 5 times that tau would be the time for the capacitor to fully charge. Tau, which is a Greek letter, tau, is R times C, and we'll talk more about that. But we will find that the intensity at any given time, which is lowercase I, intensity being varying, and we're going to take this variable with lowercase I and Q, is the initial intensity e to negative t over tau, tau being RC. Whereas the charge starts with no charge, and then we will see how the charge look like in time. At time equals 0, and we will derive the charge expression, and then we will find out the intensity expression. But it just seems like after a period of t equals tau, the intensity here drops to 63% of the initial intensity. So at time equals tau, the intensity is 0.63 of the initial value, meaning that 36% of the intensity, initial intensity, was lost, decayed in value. Now the question is, how do we derive those values? we're going to use Kirchhoff's law or Kirchhoff's rules for this loop, and actually we are going to use just the second rule, which is the rule for this loop. Let's take that, let's go around the loop and see what we get. So we have a raise in potential as we move over the battery of E, E being the electromotive force or the voltage that the battery provides. We consider it to be an ideal battery, no internal resistance. And then we're going to, if the electric field is pointing in this direction, we can say that we have a drop in that voltage over the capacitor, which is going to be equal to Q over C. And then we have another drop over this resistor, the current pointing in this direction, which is I times R. Intensity is varying, so I'm using the lowercase I. That is equal to 0. Now we know the intensity is dQ at dt, and we want to just plug that in. So we have E minus Q over C minus dQ at dt times R equals 0. One other thing that I want to point out, as we charge the capacitor, there will be more and more charges that will end up on the capacitor plates. And with that being said, dQ is positive because we'll have more and more charges, which is not the case when we discharge the capacitor, which will be the next topic that we will discuss. Let's isolate our variables. So we have E minus Q over C equals R dQ at dt, which makes dQ over E minus Q over C equal to dt over R. And then I want to integrate from time equals 0 to time equals t, as the charge on the capacitor gets from 0 to Q. Now obviously on the right hand side we have a t over R equals to this integration, and I want to use the substitution method, and I'm going to call let E minus Q over C be equal to U, and obviously we want to correlate dQ and du. So what we have, negative dQ over C equals du, and what we will have here, instead of dQ we'll have negative C du, and E minus Q over C is actually U here, right? Are you with me, guys? So what we have here in the end, we have natural logarithm of U, and we can replace U with E minus Q over C. E minus Q over C equals to negative T over RC. And then we want to take our limits from Q equals 0 to Q equals Q. So as we plug all those in, we have natural log of E minus Q over C minus natural log of E equals negative T over RC. And then what we get there, we get E minus Q over C, everything over E, is equal to E to the negative T over RC, which makes it into E minus Q over C equals E times E to negative T over RC. and what we get there, we multiply by C both sides, and we get EC minus Q equals EC times e to negative t over RC. And remember, we were looking for Q, so Q is going to be equal to EC minus EC e to negative t over RC. And we can say Q is equal, and EC, if you remember how we define Q as C as Q over the voltage, we can say that this, what we have here, is our Q final, not Q initial, because initially we have no Q, over multiplied by 1 minus E over to the power of negative t over RC. So that is going to be our expression for Q, and we can go back here and can say, number one, we say, okay, Q is going to be on Q final, and we have 1 minus E to negative t over RC. RC is our time constant. And if we want to find the intensity, intensity would be dq at dt, which is equal to, Q is a constant, we get a 0 there, and then we have Q over RC e to negative t over RC. And Q over C, this is a voltage over R is going to give our intensity, and this is going to be our initial intensity. As it decays in time, as the capacitor is charging, there will be more push in the circuit from those charges that are mounting on the capacitor plates over RC. So this is the expression of your intensity here, and that's what we wanted to prove. So we have the mathematical expressions for the intensity in an RC circuit. We have the mathematical expression of the Q, the charge mounted on the capacitor plates, and we have the time constant, which is RC, and we know that the capacitor behaves like a wire as the flow of charges are establishing in the circuit, and then the capacitor becomes like a switch as the capacitor is fully charged. And that's all I wanted to share with you guys today. Tomorrow we will do the discharging of the capacitor, and I want you to try to practice this derivation, and there will be some homework posted on our Google Classroom. Stay safe. Until tomorrow.